Welcome to the SPE Podcast, powered by the Society of Petroleum Engineers. You're listening to SPE Live, Chemical Considerations of CCUS and New Energy Development. The audio from this episode was previously recorded on March 8th, 2023. And now your moderator, Mike Fuller.
Good morning. Welcome to this SPE Live event on Chemical Considerations of CCUS, New Energy Development. My name is Mike Fuller. I'm a Senior Completions SME with Chevron, and I'm going to be your moderator today. Today's SPE Live is going to last about 30 minutes. We do encourage you to ask questions throughout the program, and you can add those into the Energy Stream chat box that you'll see there. For our topic today, our audience can appreciate that the field of new energy development has a lot of new energy sources whose development are being explored in parallel. And development a lot of those energy sources have challenges related to both chemistry and geochemistry that could benefit from the expertise of a lot of current upstream professionals within the SPE community. So before starting our conversation, I'd like to first invite you to attend the SPE International Conference on Oilfield Chemistry on the June 28th and 29th in the Woodlands, Texas. We welcome your participation in the ongoing dialogue throughout the conference program about current trends in oilfield chemistry and emerging energy topics. For the last 50 years, the SPE has brought together technical experts from the oilfield chemistry field of operators, chemical and service providers, and academia to share the latest developments in this field. It is now my pleasure to introduce our guest panelists who are joining today. Stephanie Peet is a laboratory manager for Scaled Solutions USA based in Sugar Land, Texas. She has a master's in science and chemistry from the University of Strathclyde in Glasgow, Scotland, which includes an industrial placement in formation chemistry and a thesis study of absorbent materials for water purification and CO2 capture. She joined Scaled Solutions in Scotland 10 years ago, where her focus has been on production chemical testing and analysis in predominantly oilfield applications. Our next guest is Ian Rowe. Ian is a technology manager with the U.S. Department of Energy's Bioenergy Technologies Office, within the Office of Energy Efficiency and Renewable Energy. In this capacity, Ian is responsible for assisting with the overall strategy of the office on numerous activities, as well as managing a diverse applied R&D portfolio that focuses on decarbonization of fuels and chemicals. Specifically, Ian manages projects in CO2 utilization, biochemical conversion of biomass, and carbon management. Stephanie, Monica, Ian, welcome to this SPE Live event. So we're going to start with carbon capture, utilization, and storage, or CCUS. While capturing CO2 alone presents some interesting challenges, injecting that material to downhole reservoirs can produce some additional challenges in how CO2 reacts with both the formation and some of the well construction materials downhole. So Stephanie, you're going to be presenting at the 2023 Oilfield Chemistry Symposium on some new and novel lab testing techniques to look at CO2 in the formation interface. Can you briefly describe for us some of the flow assurance challenges that may be anticipated in CCUS, particularly for storage considerations, and how we can address them with experimental techniques?
Hi, Michael. First of all, I'd like to say thank you for inviting me to be part of today's event. I think it's very appropriate that we're sitting having this conversation when the first cross-border offshore storage initiative goes live today in Europe. It's called Project Greensand. In regards to your question, there are many correlations and transferable reference points that we can take from CO2 EOR injection. However, there are still a considerable gap in our bridging our knowledge and understanding when it comes to CCUS storage. The EOR systems will display quite different flow assurance risk profiles in the sense that they are single high-pressure injection sources going into high-temperature, high-pressure reservoirs. This will not necessarily be the case for CCUS. The challenges faced by CCUS operations will include the potential of fluctuating injection volumes, pressures, and rates because it's coming from various sources. The injected CO2 will ultimately have varying impurities and quantities of such impurities, again because of the various industrial processes that it's being sourced from, and also as byproducts from the capture process. We will be injecting into storage plays at temperatures much lower than those observed in hydrocarbon-rich formations, and we also have the continued and prolonged exposure of the injection casing and the wellbore materials to the acidic CO2 compared to, for example, WAG operations. The aim here will be that once we hit go, we will not be wanting to stop at any point. So the flow assurance risk considerations are all the usual suspects in regards to scale, corrosion, hydrates, halides, geochemical and geomechanical. However, they must be approached with a different viewpoint on the conditions in which they arise when it comes to CCUS storage and injection. One example is injectivity and formation damage risk potential of CO2 hydrate formation at the near wellbore. They can form as a result of Joule-Thomson temperature drops associated with the injection of high pressure CO2 into lower pressure reservoirs, or the injection of high pressure CO2 into shallow reservoirs of sufficiently low temperatures. Now, where hydrate risk has widely been researched in oil and gas over the years, the majority of that research has been done using testing techniques which replicate its bulk formation in tubulars. It has rarely been assessed under dynamic flow conditions using core samples which replicate the porous environment of the formation. CO2 hydrates specifically have also been investigated within CCUS, but again, this is in regards to its utilisation for transportation. There's been very little assessment on the near wellbore risk that they pose. So the topic of work that I will be presenting at this year's symposium will exhibit the design, building and use of testing equipment capable of assessing CO2 hydrate formation risk and subsequent mitigation in low temperature core flood tests in the lab. Now, the initial tests conducted have used brine as a chemical carrier for the hydrate inhibitor, but what we need to consider is the fact that the only carrier that may be available during these processes is the CO2 itself. So what we must then look to do is assessing chemical product performance in this medium and developing best practice methodologies to do so in the lab before we go to the field.
No, that's fantastic. And I'm looking forward to hearing more about that study at the upcoming symposium. Thanks for that, Steph. So our next question is going to be for Ian. What are some of the key goals or specific programs that we might expect to see in the next 5 years out of DOE in the area of CCUS?
Sure. Thanks, Mike. And thanks for having me here. Always a pleasure to talk about this stuff. I would say that the department was given a pretty clear mandate from the legislative branch, was that in late 2021 in form of the bipartisan infrastructure law, which laid out a lot of different programs that are now new to the Department of Energy on CCUS. A few of the big ones are we have a mandate to set up carbon capture demo projects. This is in our new Office of Clean Energy demonstrations. And this is a significant amount of money to set up 6 carbon capture and sequestration facilities with recommendations for some to be from natural gas, electric generating units, coal generating units, and industry facilities. So we have the demo projects. There's also a significant amount of funds also in the clean energy demonstration realm for pilot of more innovative carbon capture large scale pilots. And we also have our regional DAC hubs, and that's for regional direct air capture hubs. So another $3 to $4 billion program in the Office of Clean Energy demonstrations, with the idea really here to fund hubs that can remove and sequester approximately 1 million tons a year of carbon dioxide from direct air capture. So there's a clear mandate on that both capture and removal side. And on the U part of CCUS, which is the part that I have the most expertise and experience in, is on the utilization piece. There are several programs across multiple offices at DOE, the Office of Fossil Energy, the Bioenergy Technologies Office, ARP-E, Office of Science. All of these are all the way from fundamental research all the way through demonstration on utilization to turn carbon dioxide into fuels and chemicals. Namely, there's this new consortia set up at the national labs on CO2 reduction and upgrading for e-fuels. And the idea there is how do you leverage renewable electricity and carbon dioxide to turn it into fuels and chemicals? And that can all be wrapped up into other initiatives we have at the Department of Energy, like the Sustainable Aviation Fuel Grand Challenge, the idea that we need to get up to 36 billion gallons of sustainable aviation fuel by the year 2050. And we can use a lot of biomass feedstocks to meet that need, but there's only so much biomass. We need to look to other feedstocks like carbon dioxide. So that's one initiative helping us there. And as well as back to the carbon capture and sequestration side, we have our carbon dioxide removal energy earth shot, which is around the goal of $100 per ton carbon dioxide removal by the year 2031, I believe. So there's a lot of R&D underway right now to try to hit that goal.
Wow, that's fascinating. Sounds like a wide suite of work, and we appreciate you sharing some of that with us. So at this point, since there's so many different topics under this area of new energy, I'm going to move on to talk a little bit about hydrogen. So, and Ian, this question will go to you again. So when thinking about development of hydrogen as an energy source, the first questions that really come up are related to safety and monitoring. So Ian, you had recently moderated a webinar that talked about hydrogen and some of these considerations. Can you comment either based on some of that webinar or based on your ongoing work about some of that work at the DOE to explore really specifically safety and transport of hydrogen from a chemical standpoint?
Yeah. Great question. Yeah, very important because hydrogen, while very energy dense on a per mass basis, it's extremely not energy dense on a per volume basis. So you've got to shove it in and really cram it into a vessel. And then you have something very flammable under a pressurized vessel. So the safety implications are clearly very important. I would say the leading platform we have to understand this safety and risks associated with hydrogen storage and transportation would be the hydrogen risk assessment model. It's a state-of-the-art hydrogen safety model and data platform, and it really is built to put all of the R&D that has gone on at the national labs and everywhere else associated with understanding those risks into the hand of industrial partners and researchers. So this is led out of Sandia National Labs, and it takes information like the frequency and probability data for hydrogen component failures, like embrittlement, some models on hydrogen gas and flame behaviors, what happens to gas plumes as they escape from certain holes or fissures, and really taking all of that information, including ignition probabilities and stuff, into a model so that somebody can assess the risk of it if they have a good understanding of the model. It's not to designate whether or not a certain project or activity is safe, but just to add more understanding so everybody knows the risks involved. There's a good example of this at work is the team at Sandia had a collaboration with the state of Massachusetts to understand the risk associated with transporting hydrogen in some underground tunnels there, because the obvious risk there is if hydrogen's leaking, it's in a tunnel, does it build up and explode, and do you have a big problem? And working together with Sandia, they were able to get a real understanding of the risk there and realize that there's actually a lot of room to do such an activity with some relative safety.
That's great. Thank you. Thank you for sharing that, Ian. And certainly, I think when it comes to some of the tunnel and construction challenges, certainly in the upstream oil and gas space, there's a lot of expertise in that already. So I think there's definitely some great synergies that I'm glad that some of the folks who have joined us online can learn about regarding that work. So fascinating. Thank you for sharing it. I'm going to do a quick pivot a little bit to talk about kind of something that I think is really important for the broader SPE audience, specifically some of the young professionals. And in that, I want to talk a little bit about skills gaps and careers in the development of new energies. So Stephanie, I'm going to pick on you first, really, ultimately. So as a young professional, what would you say are some of your expectations of kind of responsibilities you might face and maybe skills you might need to develop related to energy sources, new energy sources, as you progress in the future?
Okay, well, first of all, I'd like to say thank you for considering me a young professional still. In regards to experiences and responsibilities, my background is a chemistry degree. We had lots of choices on what we wanted to specialise in, but I could never decide. So I went for the general one, and I just think the transferable skills that a science or engineering degree provides someone just gives them so much options in the future for what they want to focus on. The only PhD I ever considered doing was a CCUS one provided by the University of Edinburgh. They've been providing that for over 10 years now. But PhDs aren't necessarily for everyone. So I think just in regards from a scientific point of view for young professionals, I think it's absolutely invaluable of just getting your foot in the door somewhere and getting these strong background base knowledges in regards to best practice for work in the lab, good lab practices, all that kind of thing. It builds up strong foundations for when you do want to start focusing on various different energy streams and things like that. And then it's just a case of being up to date with what's going on in the industry. It's all very much independent research and reading articles and seeing what grabs your interest.
Very good. So I think it sounds like you're saying that, at any point in your career, the key is to be kind of a lifetime learner. And I think to continue to stay fresh in what's being done and to kind of try to adjust with that. So that's a great share. If it's okay, and Ian, can you give me a thumbs up that you can hear us? Good. So with you back, we're going to ask you one more question also in the similar space of my previous question on careers and career development. So I'm familiar that DOE has got an internship program for early career professionals to learn a little bit or to dabble in the space of new energies. Can you tell us a little bit about that program? And then we'll get to some audience questions.
Sure, Mike. I'm also noting that you didn't call me a young professional, so I'm going to remember that. But I would say DOE has a plethora of different programs to try to get new people involved, people fresh out of school, or even people already established in their career who want some experience in some different energy topics. First, I would cite the student ORISE program, Oak Ridge. Apologies, I forget what the acronym stands for, but it's an internship program specifically focused at students just out of school. And I've worked with many interns through that program, and they're people that I consider friends to this day, and they've gone on to have very successful careers in either the national lab system, out in industry or academia, or at DOE itself. So that is a lucrative route in. There's also a lot of fellowships regarding a lot of routes for things like the AAAS fellowship, the Presidential Management Fellowship. These are all things that I would explore if you're a young professional looking for a way to get involved with DOE, as well as we've plenty of technology commercialization type activities where the goal here is really to connect people in industry or academia that have a new technology, but they don't have the funding to they need more support to keep it to get it out into the commercial sphere. They can come in, work with the national lab, get some support from DOE, and they can move that technology forward if they can get some R&D funds to do that.
Yeah. Fantastic. And thank you for sharing that. So I'm going to pivot at this point to some questions online. And the first question we can put to just about anybody. So the question comes through LinkedIn, and it is, what are some of the most promising chemical processes for CCUS and new energy development? And really, what are some of the key challenges with scaling them up for large-scale implementation? So if anybody wants to tackle that, I would encourage you guys to take a crack at it. Ian, do you want to go ahead?
Sure, I'll go first. And Mike, I'll be honest, I lost you in the middle there for a second, but I think I got the question. So in terms of near term, I'll focus on the utilization side. Near term routes are really helped by recent things from the Inflation Reduction Act. There was a tax credit in there that gives up to $3 a kilogram for the use of renewable hydrogen in a pathway. So you can envision a utilization strategy that takes carbon dioxide and combines it with hydrogen to make a fuel. And the fact that a lot of fuel pathways that use CO2 need in the order of 2 kilograms of hydrogen per gallon of fuel, you can see how this could very quickly scale up to be quite a lucrative tax credit incentive. So I would say that look for things that are already established technologies. For example, reverse water gas shift is an established technology that we know how to do that need a lot of hydrogen. And there's ample supplies of carbon dioxide out there. So I could see a near-term opportunity for that to really take off in routes like that.
Fantastic. Thanks for sharing that, Ian. I've got another question that popped in as well. Let me make sure I've got this right. Okay, so this question actually is going to go to Stephanie, and we're going to be back on geothermal a little bit. So you talked a little bit about flow assurance as well. So can you briefly talk about some of the flow assurance challenges we might expect unique to geothermal wells and how we can address them using experimental measures?
Thank you for the question. So for the Geothermal, what we're basically looking at is the other end of the extreme temperature spectrum. Previously I was talking about low temperature for hydrates, now we're looking at the higher temperatures which will be experienced. This will result in much quicker scaling kinetics, driven by the temperature differences between the saturated reservoir brines and the cooler surfaces they'll experience during processing. This poses a higher risk coupled with the difficulty to manage it chemically because scale inhibitors will thermally decompose at such high temperatures. One of the main scaling risks we anticipate to experience is the formation of amorphous silica scale. It's anticipated to occur in almost all conventional high enthalpy geothermal operations along with calcium carbonate. This scale may be the main issue limiting the extent of geothermal exploitation. It's very difficult to inhibit effectively and it's insoluble in any practicable solvent. Its formation must be prevented by controlling the degree of temperature fluctuations that are experienced during the fluid heat extraction processes. Now, the standard testing equipment available in the oil and gas industry in regards to qualifying performance and application of production chemicals max out at around 200 degrees C. Now, the equipment, the temperatures, that geothermal will experience will be much higher than this. So any chemical products that will be applied in the field to assist in flow assurance or integrity preservation need to be tested appropriately in the lab at these temperatures before any field application.
Very good.
So what this requires is equipment redesign and material selection, basically, at the lab stage.
Very good. Thank you for sharing that. I think with that, we are at the end of our SPE Live session. So first of all, I want to thank our panelists, Stephanie and Ian. Thank you guys so much for your insights. And to our audience, to learn more about these topics, I do encourage you to come to the upcoming SPE International Conference on Oilfield Chemistry this coming June in the Woodlands, Texas. So again, to everyone, thank you for your questions and comments and for joining us today. We'll see you next time.
Thanks for listening to the SPE Live Podcast. For more content, visit the SPE Energy Stream, the industry's digital pulse, at streaming.spe.org. If you enjoyed today's show, don't forget to subscribe and review. Join us next time on the SPE Live Podcast.